sure yourself. But as a manufacturer, I should give you something. It doesn't depend on the dimension. You want to select 1,000 turns, select 1,000 turns. You want to select 5 turns, select 5 turns, right? I should give you something. This is a magnetic property of this material I'm giving you. Now you are the design engineer. Go do whatever you want to get to your lambda I, right? And there are different applications, different projects. Everybody is different from the other one. This curve, it doesn't depend on any physical dimension. Look at here, physical dimension, L and A. And also, N is kind of physical dimension because it's based on how many turns you're going to put there. If you go look at all the magnetic materials, they give you the BH curve, not this one. This one is your design. You know what I'm saying? Then you select the core, how much is the cross section, how much is the length, how many number of turns you want. This one become a specific design, right? It become a 2 millihenry design inductor. It becomes, I don't know, Apple inductor design. They have it. Look at these small power supplies Apple has. They're coming with a very small inductor. If you look at the Dell power adapters and Apple power adapters, look at both of them. They're both simply they're a charger. You know, those on the Power Electronics, they will teach you what's a charger, very simple charger. But what Apple has done, you know, with the different techniques, it has made it very small. Very small. You know, power supply is not heavy and bulky anymore. So this is your design. Companies, they give you this one. They say, hey, go whatever you want to do. Design whatever you want. I'm going to give you the BH curve of this one. And doesn't matter who is working on it. For everybody, for this material, BH curve is this one. Use that one. Now, the next one we're going to go, let's do I'm going to look at the leakage inductance a little bit to see what is the leakage inductance. You're okay, I'll go non-stop, is that right? You're fine. We'll go non-stop to finish it, you know? Basically, what we calculated here, they call it magnetic inductance, or because look at here, the flux here is going this way, right? The inductance is happening. Where was the inductance? This inductance is happening because of the flux inside the core, right? So let's come back here. How we define the inductance? N phi over I, right? Because of the flux inside the core. But how about, let's go back to electrical circuit because we understand those one better. So if we have a voltage source here, and we have a wire here, just I'm making it perfect wire, it is short. You're not going to have circuit like this, right? But what is going to happen, all the current is going to go through here, right? And there's a very small resistor for the wire, right? Very small resistor for the wire. But in reality, air around the wire also has some resistor. This is the R1 and this is the R air, right? Air also is a conductive material, but very extremely bad conductive material, right? But still, then you look at it, this current is coming here, I don't know, more than 99.9999999 coming through this one, right? And small value of the current, very, even you cannot sense it, right? It's going through the air. They call it leakage current also. We talked about the corona in the power system, if you remember. We said when it's a very high voltage system, in the rainy days, if you look at those high voltage, tower, we can see kind of light, blue light around the conductor. They call this is the current they are leaking to the air, because the air become a little bit conductor around those wires. So here the same thing, even all these wires here, but because this leakage current is extremely small, this will forget this one. There is nothing here, right? The same thing here. If this magnetic material is a perfect material means mu is infinity or 0. Which one? Infinity, because reluctance will be 0, right? Yeah. Is L over mu A, right? If it's the perfect material, mu is infinity, so basically the reluctance of the material is 0, right? If this one is a perfect material, which we don't have that kind of material, but if it's a perfect material, all the flux is going to stay in this core, right? But if it's not, air also, there is air here, right? Some of these fluxes say, hey, I'm not going to go that way. I'm going to go here. I'm going to go here. They call it leakage flux. They call this one leakage flux. So if we look at the system now, I said I'm going to draw the electrical, the magnetic circuit for this one. I have a source, is Ni. I have a core, it has Rn, right? This is or R, whatever. It could be the magnetic material and air gap. But look at here. Look at here. I want to see how I'm going to design this one. I'm going to draw that one. Some of the flux is going here. Some of the flux is coming here. I'm going to model these two together. Some of it also goes this way, right? So basically, if you look at it, there is another R here, right? This is the leakage. I'm not sure what you call it here. Here I call it RL, or leakage. If you compare these two, this is the phi L, phi leakage, and this is the phi M, magnetic, flux. So if you compare these two, our leakage is very, very bigger than RM. And most of the time, we ignore RL. We say, hey, like electrical circuit, we say, hey, forget RL is huge. There is no flux going there, right? But let's see how we can calculate the inductance for this circuit. How much is the inductance here? So if I'm going to go with that equation, right here, if I'm going to go with this equation, look at here. These are like a parallel, right? There are two parallel. Can I put it like this? I say this phi is going to be phi m plus phi m, right? Phi is equal to phi m plus phi l. Now, lambda here, lambda, how much is the lambda? N phi. So lambda is going to be n phi m plus n phi l. How much was L? L was lambda over I, right? L was lambda over I, right? So let's put it here. L is going to be n phi m over I plus n phi l over I, right? There are two terms. I'm not going to go very much in detail, but what is this? Yeah, let's continue. Let's continue. How much is the phi m? How much is the phi m? Let me write it here. Phi m, isn't it Ni over Rm? Look at here. How much is the phi m? This voltage divided by this resistor, right? How much is the phi L? Phi L, sorry, I should go a little bit higher. Phi L is this voltage divided by this resistance, right? let me put it here. I'm going to write it here. What I put here is L is equal to N phi M over I plus N phi L over I. What I put here, I said how much is the phi M is the Ni over Rm, and how much is the phi L is the Ni over Rl, right? Because I use this very simple equation in that circuit. Now, let's calculate that. I'm going to replace this one. It's going to be N squared over Rm plus N squared over Rm. Right? This is the same equation we had over there. N squared over R, right? This is a magnetic inductance. We call it Lm. Why? Because it's happening because of the magnetic flux. The flux is going through the core, right? The flux is going through the core. It's generating this inductance. And we call this one leakage inductance. Lm. For most of the time, we assume LL is 0. We assume the leakage inductance is 0. But it's not. This is different from electrical circuits. Electrical circuit, almost 100% of time, we say forget the leakage current. But in magnetic circuit, it's not like that. If you have an induction machine, if you have a transformer, if you have a synchronous machine, all of them, they have a leakage inductance. Already you know about the transformer, you have a leakage inductance, from the power system course we have. But this is in general. Inductance is the magnetization inductance plus the leakage inductance. But LL usually is much, much, much smaller than LM. Just keep in mind, LL usually is much, much smaller than LM. Now, we finish this part. The next part is, how about if we have two windings? Hold on, before going there, I want to go through one more equation for one winding, and after that, we go to the two winding system. I'll give you the first homework tonight, and the due date, we'll work on the due date to see when the due date, we're not have enough material. Before getting to the, because all we talked up to this point is only one winding, we may have two windings, three windings, we want to know what's the energy, what's the inductance in the circuit, those kind of things. But before going to that point, I'm going to review just one more thing here with a single winding. If we have a single winding, let's say, I don't care what's the shape of this core. This is the flux phi here, and we have E here, and N, and I. So, if this flux is a sinusoidal flux, it could be any other shape. It could be see, sinusoidal is like this. This is a phi n, phi t, and this is a phi n. Or, you may see it in the homework, it's going to be something like this. A square wave. But this is a 0.5 t, and this is a t, and this is a phi m. Average of phi should be 0. Phi cannot have any average. If it has an average, it's going to saturate the core, and it's going to kind of make the circuit unstable. Could be another shape. What I'm saying is average 0. Now let's focus on this one. When we have a sine wave form. So E is equal to N d phi over dt. Just let's replace it from here. So E is going to be, and let's say E is connected to a voltage source like this, right? Vrms, with a Vrms, the voltage is Vrms, and frequency is F. You have a AC source here. It has for example, 110 volt, and the frequency is, for example, 60 hertz, right? We know the Vrms and the F. I want to find out what's the relation between the phi m and the voltage I have here. I want to find out the relation between the maximum flux and the voltage. So E is called this one Vs. Vs. E almost is equal to Vs. I'm going to give it to you homework when you have the homework. I'm going to leave that one for homework for you guys. Ideally, V and E and V, they are not equal. E is here. Ideally, this voltage and this, practically, this voltage and this voltage, they are not equal. Why? Because there's a little resistance here, right? There's a resistance between these two, right? So, but right now I'm not considering that part. I'll leave that one for the homework. You guys can work on that one. So, E is equal to Vs, and E in this one is equal to N dphi over dt. Let's replace them. So Vs is going to, let's take a derivative of this one, is going to be phi m omega, right, cosine of omega. Am I right? And times it. There's n here, right? So this is the maximum of the voltage, right? This is the Vm. So basically I can say Vm is N phi m times omega. 2 pi f, right? 2 pi f. So phi m, I can replace it with A Vm. A Vm, right? So basically Vm is equal to N A times 2 pi times F Vm. I'm going to put it right in the middle. I said Vm is equal to Na times 2 pi times F times Vm. And then you know Vm is equal to the square root of 2 Vrms. Right? That's a sine waveform, right? If you replace everything and simplify it, you're going to get Vrms is equal to 4.4.4 NFA Vmax. This is a very, very famous equation for sine waveform. Vrms, just double check it, to make sure I didn't make any mistake in the calculation. But I know that a final answer, the final answer is correct. And Vrms is 4.44 times N times F times A times Vmax. So what's the good things about this equation? Can somebody tell me? No, always we were talking about the Bm. How much is the Bm on the BH curve, right? We said we don't want to pass this point and those kind of things, right? If I know the voltage connected here, I know the frequency is 60 hertz. I know how many turns I have. I know how much is my cross section. Quickly I can calculate based on the Vrms. I can calculate how much is my Bm, right? Or the other way. I can do the other way. For you guys, I'm not going to go over the hysteresis loss and those kind of things. You can check your notes from the power system class, if you need to get, because maybe in homework you see something about hysteresis or those kind of things. Just go check the notes from the previous class. Previous class we had it last quarter. I'll try to avoid that one because we test you on those ones. But maybe in the homework you see something about hysteresis, those kind of things. All equation you know already about that one. For example, just do it as practice for yourself. If the waveform of phi is like that, or the voltage is like that, find out what's this equation. I'll cheat. I'll tell you the answer. It's 4. Instead of 4.44, it's 4. But go prove it. If instead of sine waveform, it's a square waveform. So you can find out how much is that. Now, we are done with this part. I'm going to go with the system with 2 windings. So I'm going to go to the system with 2 windings. Do this one, read this waveform for you. Let's check that one. So yeah.